Good day everyone, my name is Mirza bin Mokhtar and today I will be explaining the concept of electronic equilibrium. In this presentation, we will explore how energy is transferred and absorbed when high energy photons interact with matter and how electronic equilibrium affects the relationship between the Kerma and absorbed dose. We will also look at the real world implication and challenge of calculating absorbed dose in various situations where electronic equilibrium may not be fully achieved. Electronic equilibrium is an important concept in radiation dosimetry that helps us understand how energy is transferred and absorbed when high energy photons interact with a material. When electronic equilibrium is reached, the energy transferred from photon to electron is fully absorbed by the material, which allows us to directly calculate the absorbed dose. However, in many situations, this balance doesn't happen, making it harder to calculate the absorbed dose accurately. Kerma is the energy that photons give to electrons as they pass through the material, while the absorbed dose is the energy that the electrons deposit in the material. The key point is that the Kerma happens where the energy is transferred to electrons, and absorbed dose happens where the energy is deposited into the material. When electronic equilibrium exists, the energy transferred to electrons is completely absorbed by the material, meaning the absorbed dose can be directly calculated from the Kerma. But if there is no equilibrium, it's not that simple. In the simplest case, where the photon beam doesn't lose energy as it moves through the material, the number of electron tracks created by the photon stays at constant at each depth. In this case, the absorbed dose increases with depth, reaching its maximum at a certain point. After this point, the Kerma and absorbed dose become equal. This region is known as the build-up region. Once we move beyond this build-up region, the absorbed dose equals the Kerma, assuming no loss of energy. In more realistic situation, the photon beam does lose energy as it passes through the material, which is called attenuation. As the photon lose energy, fewer electrons are set into motion deeper in the material. This means that the absorbed dose initially increases, but then starts to decrease. In this case, the relationship between Kerma and absorbed dose becomes more complex. The absorbed dose will still have a peak, but will always be higher than the Kerma curve beyond that point. When electronic equilibrium is achieved, the absorbed dose can be calculated using this formula. D is the absorbed dose, absorbed energy is the energy transferred to the electrons, G is the energy lost due to a type of radiation called Bremsstrahlung, and K is the Kerma. This formula works when electronic equilibrium is reached, meaning all the energy transferred to the electron is absorbed by the material. In real-world situations, electronic equilibrium is not always reached. For example, at the boundary between two different materials like soft tissue and bone, electrons may travel from one material to the other, which makes it harder to reach equilibrium. This also happens with high-energy photons, where the photon beams is significantly attenuated. These factors make it more challenging to calculate the absorbed dose accurately in these situations. In conclusion, electronic equilibrium helps simplify the relationship between Kerma and absorbed dose. When equilibrium is reached, we can directly calculate the absorbed dose from the Kerma. But in many real-world situations, such as when photon attenuation happens or when material with different properties interact, achieving equilibrium is difficult, making the calculation of absorbed dose more complex. Understanding electronic equilibrium is crucial for predicting how materials and tissues respond to radiation. That's all from me. Thank you.